Okay, so now what we're going to do is look what happens when we move beyond the third period. And this is interesting because we now start filling up D and F subshells and things get a little bit weird. So beyond the third period, orbitals don't fill in an obvious way, and it's for that reason that I mentioned before. Because of the bunching up of our energy levels, our shell levels, when we put in the splitting into the subshells, things start getting muddled up. And probably the real obvious one that we first see is that the 4s ends up coming below the 3D, which is completely sort of non-intuitive. So fortunately, there's a way of keeping track of all of the weirdness that happens along the way, and it's called it's through the use of what we call the Aufbau diagram. So what you do is you write 1s through 7s in the first column, and then at row 2 you write 2p down to 7p, and then in row 3 you write 3d down to 7d. There's no reason to cut it off, you can keep going. And then in row 4 you write 4f down to 7f, and that gives you the kind of the general layout. And then you put these diagonal arrows in, and what happens is you start placing electrons into these subshells. When you get to the end of an arrow, you go and start the next one. And that gives you, or takes into account, all the weirdness that you're going to see along the way. And so you can see here that this diagram prompts us that we would fill the 4s, and then we fill the 3D. And then down here, we fill the 5s, and then we fill the 4D. So it takes into account any weirdness that happens along the way. That it starts doing something similar when we get down to the F. So here we fill the 6s, then we do the 4f, then we do the 5f, and then we do the 6p. So all of those kind of non-intuitive things get taken care of through the use of this diagram. So you should kind of have a copy of this diagram handy when you're working on electron configuration problems. You should also know how to use it. It's pretty simple. You just follow the sequence and keep in mind that in an S subshell, you put 2 electrons. In a P subshell, you put 6 electrons. In a D subshell, you put 10. And in an F, you put 14. So what happens? Let's have a look at what happens is we're putting some electrons into these D subshells. So in period 4, we're going to finish off the 4s orbitals or orbital, and then we start filling up the 3D orbitals. So potassium is the first member of the 4th period. It has electron configuration just written in the condensed form here, argon 4s1. Next to potassium is calcium, it's argon 4s2. And then now we begin filling up the 3D. Now the 3D can take 10 electrons, so we're going to kind of do this in a fairly prompt manner. And so here we go, scandium is 3D1, titanium is 3D2, vanadium is 3D3, chromium is 3D4. Whoa, hang on a minute, chromium is not 3D4. We're going to have to come back to that in a moment. Okay, so chromium should have been 3D4, which means manganese would be 3D5, iron is 3D6, cobalt is 3D7, nickel is 3D8, copper is 3D9. It's not 3D9 at all, it's 3D10. So copper is a weirdo one as well. So this should have been D9, which means that will be D10. So what we see is there are 2 exceptions for chromium and for copper, and you do need to memorize these. And what's happened here, instead of it being 4s2 3d4, what we see has happened is an electron has been borrowed from the 4s subshell and put into the 3D to give us the configuration 4s1 3d5. And the same has happened for copper. Instead of it being 4s2 3d9, which is what we might expect, an electron has been stolen from the 4s subshell and now has been moved over into the 3d subshell. So there are these two exceptions in period 4, and we do need to know them. So what we see is chromium has the electron configuration 4s1 3d5, and it's also worth noting that molybdenum, that is immediately underneath chromium, also has a similar ns1 n-1 d5 configuration, except for this would be incremented by 1. So this is 4s1 4d5 for molybdenum, and then copper has the configuration argon 4s1 3d10 instead of 4s2 3d9, and then the elements that are underneath copper also follow that pattern where they are ns1 parentheses n-1 d10 rather than the expected s2 d9. So we do have to keep in mind these exceptions. For the copper group, it's the whole column. For the chromium group, it's just molybdenum underneath it that does this kind of weird thing. And so why does it happen? Well, this happens because a half-filled D subshell or a completely filled D subshell is very stable. So what's happening in chromium is by half filling the 4s, that allows the 3D to be completely half filled with 5 electrons, and that's a very, very stable arrangement in terms of energy. In copper, we have a similar scenario happening. We get, by half filling the 4s, we get an extra electron, and then that allows us to finish off the D subshell. For period 4, once we've finished off the 3D, according to the Aufbau diagram, we then go back and start populating the 4p subshell, and that's exactly what happens. So, apart from the exceptions for the copper group and those elements in the chromium group, chromium and molybdenum, it's a fairly obvious pattern across the D subshell. Once we get down to period 6 and 7, we start filling up F subshells for the first time. So that's kind of interesting. And so the elements that are going to have F electrons are these guys that are in the 2 rows that sit at the bottom of the periodic table. So remember that they're really meant to be up there, but we just put them underneath for the sake of having a periodic table that fits nicely on the page. So period 7 follows the same sort of general filling sequence as period 6, but it's sort of what you see down here is that period 7, we don't have to go out all the way out here because we actually run out of elements. So how does the order go? Well, you see on the periodic table that we have 2 columns over here, and we have 6 columns over here, and then we have 10 columns in the middle, and then at the bottom we have 14 columns. And so what's occurring is as we move across this region of the periodic table, we call it the S block or the S region. We're populating S subshells. As we move across here, we're populating up P subshells. Through the middle, we're filling up D subshells, and then these 2 rows at the bottom that are 14 across, we're filling up the F subshells. So you can actually count off an electron configuration from the periodic table. We go 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2, 3p1, 3p2, 3p4, 3p5, 3p6, 3p7, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, 4s1, 4s2, 3d1 all the way through to 3d10, 4p1 all the way through to 4p6, 5s1, 5s2, 4d1, and then we can come down here. Sorry, 4d1 all the way through to 4d10, 5p1, 5p6, 6s1, 6s2, 5d1, and then we come down here 4f, 4f1 all the way through to 4f14, and then back up and finishing off the 5d, 5d10, finishing here 6p1, and so forth. So you can kind of actually use the periodic table to allow you to write out an electron configuration. You just got to kind of count it off, if you will, and follow where you are with respect to what we call the S, P, D, and F regions of the periodic table. So this is another diagram that's worth kind of keeping handy when you're trying to write out an electron configuration. Okay, so what we talked about here is that in period 4, we see D electrons for the first time. There are a couple of issues with elements that are in the groups where we have chromium and copper at the top of those groups, and we have to keep in mind that elements in those groups do not strictly follow the sequence indicated by the Aufbau diagram. Once we get down to period 6 and 7, electrons, that's meant to be electrons, begin to fill F subshells for the first time, and so we have up to 14 electrons that can go in one of those subshells. And then the final point to make is, if you want an alternative to the Aufbau diagram, you can, if you keep track of everything, just count your electron configuration off the periodic table. Okay.